Okay. So did you notice the supports on this dude? And notice the measurements are in pounds and feet. So that 8, 20, and 12 are feet. I just didn't write that in there when I made this drawing, but notice it's supported in kind of an interesting location. So it's like cantilevered out in both directions. And then it's this, notice the units, 312 pounds per foot. So that's a continuous load or a distributed load, which is almost always the way it is. Occasionally you'll have a point load. And by the way, that point load could be a post because maybe that's cantilevered out and that's a post that's holding up a roof over the top of it or something. And that roof is, put 720, 780 pounds there. So that's not that weird. Okay, cool. Well, first we got to find, and I should have told you to do this while I was gone, but I wasn't thinking, we got to find the reactions. And man, interrupt, like this is the backbone of like what you do as an engineer, which is why we're not skipping. So we got to find the reactions at A and B here. In other words, how much weight are they going to support? Because there are forces that aren't here. And remember, the concept of statics is the idea that, well, look, all those forces are pushing down. Well, then that thing's going to go down and the beam's not, it's just going to be falling through the air. There's no weight on it at all. If A and B are not allowed to push back, and you may notice that I drew those as walls. I mean, they're little, it's not a point. It's not the sterile. And he alluded to this, by the way. He was like, always talking about how, hey man, what if that's sitting on a triangle? And he's like, what? Stuff doesn't sit on triangles. Well, I'm drawing it realistic. Like that's a wall sitting right there. That's the top plate of a wall. And so, okay, great. Well, that means, of course, we got some kind of a force here at A. And actually, you get ahead of me and figure this out. I've got a force of A and a force of B right there. And I should know what those reactions are. What's the method for doing this? What do I have to do to get going here? Yeah, that's exactly right. Because you can see there's way more weight on the left than there is the right. So A is going to have to work harder. Notice the pounds per foot, 312 pounds per foot, and down here 20 feet. If I take 312 pounds per foot times 20 feet, I get, did I write that down somewhere? No. 312 times 20, 6240, thank you. And notice that turns into pounds based on the units. So that's how many pounds you have there. And then you have 780 pounds. So if I add that up, that's 7,020 pounds going down. So A and B are going to have to push back at 7,020 pounds. But the problem is, well, this is kind of like what we talked about recently. It's like an indeterminate load. How do I know which goes to each one? Well, thanks to the moment calculations, I have a way of doing that. And we said it doesn't matter whether you take the moment around A or B, but if you pick A or B, that'll take one of them out, right? So I can say, okay, cool, what's happening around A? Well, would you agree 780 is a distance of 8 feet away from A? So that's going to cause the beam to rotate. What am I doing wrong? And then 312 pounds per foot is actually 6,240 pounds. How far is that away from A? Because it's uniform, it's 10 away because it's right in the middle. So we're placing that 312 pounds per foot with just one load, right? And it's going to be right in the center of that 20 feet. So it'll be 10 feet, and that's 10 feet away from A. There we go. Yeah, like I got to think about direction. Do you agree one of those is trying to get it to go clockwise, one's counterclockwise? If we stick with the conventions, then 780 is actually trying to get it to go to counterclockwise. And so that was actually positive, but this second one here would be negative. And then the only force left is force of B, and force of B is also trying to get it to go counterclockwise. And it's a distance of 20 feet away from A. And that's it. That all has to be 0. Now, one little thing I'm leaving out of this that's a part of the real world is that beam is not weightless. Every time you draw one of these, there will be arrows all the way across it because the beam might weigh 40 pounds a linear foot. And so it'll say 40 pounds a foot all the way across it. So I'm leaving that off here just out of simplicity because this is already hard. But their beams have weight and you can't ignore that. It's not a difficult thing to include. It's just yeah, it's just those arrows, except it would go all the way across and it might say something like 40 pounds a foot. And so I'd say, oh, 40 pounds a foot. How big is that beam? Oh, it's 40 feet long. And I would put it right in the middle of it and I could add it. It's not like it's that hard to add, but But the weird thing about it is notice you have to choose a beam in order to know that weight. If I choose a bigger beam, then the weight goes up and I got to do it all over again, which is why, you know, doing it by hand like this, nobody does. So I can actually change the beam in BC Calc and it'll just kind of say pass, you know, if you will. We're just kind of figuring out the details. Okay, sweet. So if I solve that for force of B, I get 2808. And then I could repeat this with the sum of the moments around B, but since the vertical calculation, the sum of the forces just in the Y direction, now that I only have one thing left I don't know, it'd be easier just to say, well, you got 780 that's going down, you got 6240 that's going down, and you just discovered that the force of B is pushing up at 2808. Maybe I'll write force of B in there and cross it out. Force of B is up and force of A is up. And by the way, do you notice we don't know for sure if that's true? Would you agree if this 780 over here was like 78 million pounds, does it make sense that it would lift up off of B and actually force of B would be going down? So we're just kind of assuming, but notice in this case, everything is pushing down and 780 is not that big. And so you were probably right that those two arrows are going up. But just remember, if you get a negative, it just means, oh, I guess it's the opposite of what I thought. That's kind of cool. So I didn't start with that equation because, as I said, that's indeterminate. I can't determine how much of each one. But now that I know, thanks to the alternate equation we made, now that I know that that's 2808, then I can find the force of A to be much easier, to be 4212. As I often say, stop. Does that make sense? Why does that make sense? Or maybe it doesn't. Maybe I blew it. Yeah, you got that 780 over there. And so A is kind of doing all the 780. And by the way, would you agree that 780 is actually making B's job easier? Because it is actually lifting it up a little bit. Now 312 is not letting it go up in the air. But not only is 780 over there working A, but it's actually lifting it off of B. So that actually does make a lot of sense. So that's pretty cool. You've got to do that. You've got to get those reactions. I won't go down this road, but that means it turns out that around here, soil, and I've told you this, but soil will hold up 1,500 pounds per square foot. So does it make sense? I need to figure out, well, if that was 4,500 pounds, does it make sense that'd be 3 square feet? I need 3 square feet of concrete underneath that all the way down through the house. Wherever that is, it's on the second story, whatever, that's going to put 4,000 pounds down on something and it better be able to handle it, right? So in the case of taking it all the way down through the ground, I'd need a 3 square foot square down there roughly. And then I would know, okay, the ground will be able to hold that up. So that's a powerful calculation we made right there, as well as allowing us to continue with what we're doing. Okay. Sweet. Now let's go on to shear. Okay. So what I'm going to do is this. I'm going to say, okay, well, let's consider this chunk of beam right here. And we're going to go from here over to wherever that cut is. And we're going to let X be everything from, well, 0 to 40. So X is going to be everywhere. We got to do all of this stuff. And because I chose to work on the left, then I do have that 780 over there. But see where it gets interesting is the 312 or the 6240 there? Well, it depends on how big X is. If I let X stay between 0 and 8, then it isn't there, right? But as soon as I get past 8, then all of a sudden the 312 is there. And then when I get past 28 feet, then it's gone again. So it turns out there's 3 sections to this. Like there's 3 different answers. You got to get all 3 of them separately. It's not just one equation that handles all of them. And so, well, let's just play with that first part. Now you may remember the conventions of signs here. Down is negative, so it's that 780 is negative. But to keep everything working correctly, whether you do this on the left or the right, we actually decided to call shear, which you may remember is V. don't know why it's a V, that it would be down. And if we did the right section, then we'd actually aim it up, and that way we would get a positive answer on both sides instead of a negative on one and a positive on the other. And then we said moment actually goes up, but I'll leave that off because we're not doing moment right now. Well, let's think about this then. We'll notice there's only two forces here that are vertical. Shear is just vertical force. That's all it is. How much vertical force, how much ripping motion in the vertical direction is there? Well, as long as I stay between 0 and 8, then I just have the sum of the forces in the y direction. I think I'll even take the time to write that out. I've got 780 going down, and that shear is drawn down, so it'd be negative. That equals 0. So that means shear is actually equal to 780 the whole time, everywhere. Do you understand that? Like if x is 1 foot, 780. If x is 2 foot, 780. 3 foot, 780. Now, again, as I said, that won't be the case in the real world because there will be a continuous load because of the weight of the beam itself on it. But we're simplifying this a little bit. So that's just 780 all the way. Now, where it gets confusing is what happens when you hop past that? What happens when you jump into the, and notice I'm saying not 8 to 20, but 8 to 28, because remember, we're starting from the left the whole time. So from 8 to 28, now all of a sudden that 312 gets in here. And well, this gets a little more complicated. So let's just pretend, and maybe I'll draw this in over here. Let's just pretend we're, right there. Here's our chop. So there's our X, and so we're right there. Our cut's right here right now. And maybe I'll even take the time to kind of, nah, I don't think I will. In the interest of time, I'm going to go a little faster. So I'm going to do the same thing because, it's just some of the forces in Y. Well, I still have my 780 in there, and I still have shear going down. Nothing has changed about the drawing that I made here. Does that make sense? But here's where it gets interesting. Now, don't you have, well, some of those arrows up there? But the question is, how many of them? A second ago, didn't we take 312 times 20 to see how much it weighed? But is that 20 now? Well, it depends on where you are. You see what I'm saying? Like, look where I am right now. Would you agree that's probably like 6 feet over? So it's 312 times 6 feet. That's how much. And that's also down. So it's like 312 times 6 feet, if you will. But it's like, what do I put there in place of 6, though? How long is that? And it's kind of X, but kind of not. What if I said X was, say, 12 feet? Then how much of that distributed continuous load is there? 4, because you're 12, which is 4 feet past. It's 4 feet. So you see how you're actually taking that 12 and subtracting 8 to see how much of it is actually there?
It's 12 minus.
That's exactly right. Instead of 12 minus 8, I'm going to say X minus 8. Caesar, those pages are right over there if you want one. You see that? And now that's it. Now see what's cool this time though is I'm not going to get an answer like V equals 28. Or V equals 780. I'm not going to get a numerical answer because it depends on X, where X is. The further over I go, the bigger, the more force it'll actually be. But if I go on to solve this for V, let's see, I have V equals, because I add V to the other side, and then I have negative 312 times negative 8 minus 780, which works out to be, can I write this down? Which works out to be 5928. No, I don't think I know that. Let me think about this for a second. I got to push buttons for a second. $312 times 8 minus 780. 1716. Don't write this down.
That's how. Because you get the negative 312 distributed on the top side.
Yeah, negative 312 times negative 8 would actually be positive. So I have 312 times 8, which is 2400 something, and then I have a negative 780. So that's where I get 1716. Um,
312x minus. I guess we still do have negative. Oh, with negative field.
But suppose the on the other side can be positive and the top part is less than. And then negative 312 times negative 8 turns into a positive minus.
Oh.
780.
yeah. Okay, so there's something missing. This is great. Everything is great, except for there's something missing from this. I don't have all the forces in there. Anybody see them? Yeah, didn't I pass force of A? Forgot that one. All right. So on purpose, I'm gonna go leave it in red, like, oops. So I did that on accident. I think you can see that wasn't on, because I'm staring at what I'm doing this differently than I did when I made sort of the key for this. And I wasn't getting the same answer as I was getting, and I was trying to decide, because there's nothing wrong with what I'm saying right now. And incidentally, just as a side note, maybe some of your future teachers, but like I'm figuring this out on my own, but then when I teach this, even though I'm just sort of barely understanding it, these types of diagrams, shear moment diagrams, I'm trying to teach them kind of with entirely just thinking with you out loud. And there's times where I actually understand it twice as well as I did in my office, because I'm having to explain and I'm going slow. And I was like, oh my God, that makes sense to me now. It's like, those are thoughts in my head that I'm not saying out loud. So in my case, I was just getting a different answer. I was like, oh, and I was pretty sure what I was doing was right, but I just forgot that. And notice it's not a bad idea to go back and rewrite those two numbers up above. That's why I missed them, because I didn't see them up there in my, free body diagram, right? I mean, they're there, but I just didn't write them in there. Okay, so you actually got to add 412 to that answer, 4212 that is, and you get 5928. And so that is the same as what I had before. So I'm going to leave those red just to kind of highlight that I screwed up. And so that's the equation for the 0 or to the 8 to 28 phase. Now, something interesting. Let's think about force B. Force B is 2808. Should that be in there? This is really interesting. Does it make sense? It gets there, but it gets there if the distance makes it to 28, right? So if you're before 28, it's not there. And think 27.9999999, it's not there. And then if you get to 28, suddenly it is there. You see what I'm saying? Isn't that weird? And that's exactly right. So I kind of did this on accident, but notice I said less than 28. I didn't say less than or equal to, so it didn't get there. Now, 1 second later, like a billionth of an inch later, all of a sudden, bam, that's like a totally different answer. You see what I'm saying? Isn't that kind of weird? Well, and that's kind of what's going to happen in the next section. So if I jump to the next section and say, okay, cool, let's go on now from 28 all the way to the end, which is at 40, and you got to add all that up yourself to get that. So as I work my way across, don't I have all the same stuff? It's the same exact formula. It's negative 780, and then you got V going down, you got negative 312. Oh, wait a second, let's think about this. I don't have to say negative 312 times x minus 8. Does it make sense? I actually passed over that now. I passed over that middle stuff. Can I just say negative 6240 instead now, since I got all of it? Yeah, I can. Isn't that kind of cool? Well, because I'm still considering the section. I'm considering x as starting from here. Now, could I rewrite this as though x starts from here and like have 3 separate equations that belong in each section? Yes, I can. But it's a little cooler if you just let x start from this. If you start from the left, then it's in there. You see what I mean? So is everybody cool with the fact that I threw 60, 240 in there instead of 312 times x minus 8? Because see, it's not a variable anymore. Remember, I said, hey, this only is true between 28 and 40. So I've passed all of that. Therefore, it's just 6240 and it's right in the middle. And I do have that 4212 that I forgot. And then don't I also have the force of B, which is 2808? You agree with that? And those are both up. So I got my ups and downs. Everything's cool here. Yeah, it's this. Because I got all of it. I didn't have to rewrite it with x's in it because x is bigger. And actually, that's maybe a negative of the way I'm showing this to you, because could you just leave x in there? The problem is you should get a constant for this. Like, there should not be an x in this formula. What happens if you add all that up? You actually get 0, which actually makes sense. Yeah, because there's nothing to resist that. So all the way out there, there's nothing. And there's no forces out there to resist that. You understand that? So that actually becoming 0 is actually not a coincidence. And so now I can actually draw my shear diagram. Now I see 2 shears, 780 and 0, but does it make sense depending on what x is, I'm going to get different shears? Remember, my goal is to draw a picture of this only so I can determine what the maximum shear is. And so is there some x I can pick that would change that? And again, what's tricky about this, and maybe even slightly wrong, is does it make sense I can't go to this and say, oh, well, look, if you put 0 in there, you get 5928. That's a pretty big shear. But can you put 0 in there? No, because where did that live? From 8 to 28. The only thing you can use that equation for is stuff from 8 to 28. Yeah, and this is why you graph a shear diagram. So let's graph this equation. Now, this is a great time to go to Desmos, by the way. And you're more than welcome to like take a picture of that and turn it in as a picture, print it, whatever. Because these are really hard to draw well. You actually have to draw them twice. Once to make it look terrible, and then the second to go, oh, okay, I need to change my window to kind of make this work. Let me show what I mean by that. So if I go over here and say, okay, shear time, and I don't have a room. I don't have a room for that shear diagram. So I'm going to go down here. I'm going to draw a vertical line there, a horizontal line over here. I'm going to say this is shear, which is measured in pounds, and this is my X, which is measured in feet. And I do know that I had important things happening at 10 feet, 20 feet, and 12 feet, right? Or I should say 8 feet. I'm sorry, I said 10. 8 feet, 28, and 40. That's the only places that I have forces. So I'll put 40 here. And now I got to like figure out where 8 is. 8 is 1/5. So I'm going to try to eyeball 1/5. Does it make sense? It'd be better if I got a ruler out and kind of like measured this and something of that nature. So I'm going to put 8 feet right there. And then 20 feet is half of 40, half of 40 would be there. So it's like that much further. That last distance was, it's actually 12. So I'm thinking that doesn't look right. And I'm sort of purposely maybe floundering around a bit here, trying to figure this out. Does that look about right? So this is 8 feet. This is 28 feet. Does that look reasonable? Should I move one of them? That's 12. That's not terrible. That's not terrible. And it, you know, for the purposes of what we're doing, you don't need to redraw it. Now, what did we learn? What did we learn? From 0 to 8, what is the equation? Y equals 780. Now, in my case, because I can erase, I can afford to screw this up. And I'm going to do that maybe on purpose a little bit here. So notice where I put 780. I was like, I don't know, right there. Like, I don't know where to put it. So all the way, while X is anywhere from 0 to 8, it's just a constant 780 all the way across there. Does that make sense? And then bam, I land right there. And now I switch to a new equation. What's my new equation? 5928 minus 312x. Now, you know, part of you would think, well, I have to graph this on a graphing calculator or something now, because it's like I can't rise over run 312, and it's like, but stop and think where this ends up. Let's figure out what in, I want to make a little room up here. This is why I can't do anything without an iPad anymore. Let's just do a couple of interesting things. What's V of 8? And what is V of 28 back here? Do that in your calculator real quick. What's V of 8? You throw 8 in for X, what do you get? You get what? You get 3432, which just suddenly makes me realize I made a mistake.
Yeah.
What's wrong with this? Take a look at this. I made a mistake. I could say you guys should have caught that, but I shouldn't have made it. That's not a positive 78, it's a negative 78, 780, right? Negative 780 minus V, add V to the other side, it's actually a negative 780. Okay, so great, let's go back and fix that. But that's a pretty important mistake, because what does that mean about my graph over here? Oh, it's actually down there. Like, come on, dude, focus. It's like it never happened, unless you watch the video, and then it did happen. And so what? Like, gosh, I thought it was going to be, basically it just says, bam, like you're on one side of 8, 7.99, and you're at negative 780. And then suddenly, bam, you're somewhere else. Like, what caused that? How could that suddenly change so much? Well, take a look at this. You got 780 right there. And didn't we just get done saying the force of A was 4212? Take those two numbers, 4212 positive, 780 negative, add them together. 4212 plus negative 780, what do you get? You get that same 3432 that you just got a second ago. That's why it's up there. It's not up there because of the continuous load. Would you agree that if you just barely, come on, let me zoom. Would you agree if you just barely zoom in, you're not getting much from that 312? You're like 1 inch in, 312 pounds a foot. You're not even a foot in. You're not getting anything from that. It's the 4212. As soon as you get that, bam, it just shot way up in the air. You see what I'm saying? So I did not have to plug 8 into that V equation to get 3432. I could have got it by just looking at those other two forces. Again, I'm spending a ton of time with this because I want you to have conceptual understanding of this, because it's just so freaking cool. Okay, so what that means is from here, I jump way up here. Now here's where the problem comes in. How do I draw 3438 in here? Is that what the number was? 32. How do I draw that in here? What's the problem with my graph now? You see where I put 780? It's like my graph isn't tall enough to proportionally put 34, 32 where it belongs. So it's like, oh, I guess I'll have to draw this again. Or maybe it doesn't matter. Maybe it's like, who cares? I've got it labeled, right? So for now, let's just leave it alone and we'll decide if we needed to, in this case, if we needed to change it later. Now, the other thing I want you to do is go back to this and say, tell me what V of 28 is. If you put 28 into that equation, what do you get? What do you get? Negative 2808. Now that's actually new information. Well, it's kind of new. As I said, couldn't you just take these three numbers? Since you made it to the end, doesn't it have 780, 6240, and 4212 in it? Well, at least right before force of B gets involved. If you take negative 780, type that in your calculator, negative 780, negative 6240 plus 4212, what do you get? Negative 2808. Same thing we just got by plugging into the equation. Can you tell it's working? Does it make sense that our V equals 5928 minus 312 equation is working? It's giving us the answers it better be giving us. It's working. Now, the reason I said that is, does it make sense? It allows me to graph this. So now I can go draw in and notice in this case, and I am going to fix a couple of things here just to kind of clean this up a little bit. Now that I realize, I just learned that I have to go down to negative 2808. Does it make sense? I didn't have room for that. And it was kind of screwed up before. Does it make sense if I went up to here and kind of in hindsight, if you will, put negative 780 right here, then maybe I would have room down here to kind of get something a little bit longer. So I'm down at 2808. That's not quite as tall as 3432. So maybe I'll draw it a hair less, but whatever. And you see, I'm purposely not labeling the whole thing. I'm not saying this is worth 10 and then 20 and then 30. I'm just kind of drawing in the important numbers. And so what's cool about this is it makes sense now. I can draw that line in without ever like y equals mx plus being it. I can just go over here and say, oh, it started at this point and it went down to that point. Isn't that cool? So what I have so far then is really this. I'm just moving that 8. And sometimes you'll see these graphs kind of shaded in a little bit like this, just to kind of show, you know, this is the graph we're talking about. Well, then what happens? Yeah, and then it goes to 0. So the last graph is actually just moving this thing to 0. God, this is cool. So it goes up to there, and then it just kind of flattens out to 0 across there. So there it is. Now, why did I draw this? What's the number I need to take off of this? I drew all this for one thing, and what did I draw it for? V max. Tell me what V max is.
That is the
34, 32. Do I care about negatives and positives here? No. Remember what negative shear means? It just means, did this go this way and break, or did it go this way and break? I don't care. So if that negative 2808 had been like negative 4800, I would just said 4800. That's my maximum shear. I don't really care about the direction. So you will not be asked this on your assignment because, well, I think it's terrible. They should be asking. It's like, why am I even doing this? I mean, that's why people take these classes and have a hard time, because it's like, what is this even for? And notice in the original problem, 3432 was nowhere. It's not like I can get that. It's not like I can look at this and go, oh, there it is. There isn't a 3432 there anywhere. Isn't that kind of cool? Now, there's some other cool things. Let's just play for a second. What's really cool about that location right there? How much shear is right there? There's no shear at all. I mean, like there's no desire for it to do this. Like you could have like almost no beam there. You could like connect it with a toothpick and it's not going to go snap. Correct. That's exactly right. Now, unfortunately, there will be moment there. And so the toothpick will snap this way. It won't snap this way. So we won't be able to put a toothpick there. But isn't that weird that there's nothing there? Now, can you calculate that? Can you calculate that location? I'm going to go in here and write some things in while you're trying to, can you tell me mathematically what that number is? I'm going to zoom out a little bit so you can see, and also so I can write these equations in. You should be able to calculate it exactly. There should be no guessing. Oops. God, this stuff is cool. I'm so excited right now. What are you doing to calculate it? Say it out loud, just in case anybody's choking.
Adding 3 to the left side of the side, dividing 5.
Yeah. Set v equal to 0. Solve. Yeah, what do you get? 19 exactly?
Yeah.
Sweet. So I'm going to say at v equals 0. Now, I'm actually not calculating that out of curiosity, just because, oh, let's just see if we can figure it out. I'll show you why in just a minute, but. Turns out there's actually a good reason to do this. But for now, that's just interesting. Okay, cool. We have survived a shear diagram now for a very complicated load. And you may remember from the tour we took the other day, the guy was saying, you know, the hard part of this is like trying to figure out loading, how everything is loaded. But the machinery, like BC Calc will do what we just did there. It'll just make that diagram. And by the way, BC Calc, because it did do this before, he was talking about they fixed it and made it better. It's like, well, you fixed it and it doesn't work at all now. At least it worked a little bit before. But it literally labels it just like this. It labels those key points, 34, 32, 780, and 2808. And you may remember that the beam you choose, it'll say what percentage of shear this beam is. And so notice that says 34, 32. So then you go pick a beam and you're not going to find a beam that does exactly that, but you might find one that does 4,000. And so then it'll take, oh, 34, 32 divided by 4,000. What is that? 34, 32 divided by 4,000 is 85.8%. It'll say 85.8%. And that's just telling me and whoever reviews this that, yeah, it's only using 85% of its capacity. And so that shear diagram, you won't know that number. You won't know that 34, 32 unless you draw a diagram. Now, it'll be calculated internally thanks to BC Calc being a nerd program and so forth. But it'll just say 85%. And for the average person, I would be willing to bet 99 out of 100 people will not know how to calculate that themselves. They will not know how to do what I'm teaching you. But it'll just say 85% and everybody's good with that. And again, I just want to, get this done and go kayaking. So it's not like I'm going to calculate this either, but God, this is cool. This is really neat. I mean, to think that you could do this calculation and then have material testing data like we saw them make out there that tells us how much shear different size beams will handle, and to know you could choose the right beam and just be totally confident it's not going to break. Isn't that weird to think about? Build a building and it's like, oh yeah, it's not going to break. No problem.
Yeah, that was like my question. That chunk out of I-beam, test it, figure it out. And I was like, kind of thinking in my head, I was like, that's a dumb question. They're not going to want to waste material. They want to calculate it first and then probably test it back up there.
Mm-hmm.
So,
but they're gonna get sued for $2 million if they get this wrong. So the idea that, and you watch me make mistakes all the time in calculations, and I'm making mistakes as a math teacher, not as an engineering teacher, right? It's button pushing and stupid stuff that I'm leaving out. And I've taught math for 30 years. It's like, I don't think you could make less mistakes than a person like me would make, right? You're going to make dumb mistakes. And so the idea that it's like, well, this is a $2 million mistake, plus it's just fun to break stuff. Like, let's go break stuff. You can break stuff all day after lunch. Sign me up for that. Okay, Rat. All right, let's go on and get moment. Let's see. God, I can move stuff around. This is so wonderful. I'm so excited. Okay, so I'm going to grab just so it's down where we can see it. I'm going to grab that dude, bring it down here, except for I'm going to go and throw the moment in this. Now, do you have a sense of like, why did I throw that in there? Like, did I just do that because that's what we do? Where's that coming from? I don't even remember. That's super annoying in problems that we did before. It would just like say, oh, that's 3,000 foot-pounds of moment right there. We'll just throw that in there. Like some giant's grabbing the beam and going and twisting it. What is that? That's the fact that if you take this beam, is this side, I'll do it the way it's facing you guys. Is this side of the beam actually not there? No, it is there. So can this side go down? No, because this is going to say no, right? There's a beam over there. So if this side wants to go down, which it does because of all that weight, this side's going to say, no, you're not. That's M, internal moment. That's the rest of the beam over there that's saying, you're not going to do that. And at that point, that's actually telling you how much moment is required of that beam. Is it possible that it could be required of too much? And it's like, I can't do that. And it breaks. Yeah. So we're literally calculating what moment is required internally of that beam. And we need to know what that M is for, well, every location. And again, go find the biggest one, because that's how we're going to choose our beam.
We're kind of making an assumption. We started from the right, that's 780, it's like 7 million pounds. That moment.
That's right. If we did this from the right, we would just draw that going the other. Like this is actually what we call positive counterclockwise. If we did it on the other side, we would draw it the other direction and we would call it negative. And then we get the same answer going both ways, whether we did it on the right or the left. Okay, so what do we need to do? We need to do the same thing we just did a second ago, which is like sort out what's happening from 0 to 8, what's happening from 8 to 12, same from 8 to 28 and so forth. So let's see if we can pull this off. Okay, what's happening from 0 to 8? And this time, instead of saying the sum of the forces in Y, we're going to say the sum of the moments. The sum of the moments. Around which point? Like around what point are we talking about here? Well, it's always this cut, where the cut is. I'm going to say C for cut. It's always wherever that cut is. That's what we're doing the moments around. Well, you agree that we have, well, M, which is positive, right? What else do we have? 780 for the force, X for the length. Force times length, that's moment. Is that a positive or a negative? That's trying to get it, well, to go the same exact way, which is actually positive, isn't it? So these are both positive. That doesn't seem good. So that means the moment is actually equal to negative 780x. So that means the moment isn't just constant all the way across there. It depends where you are. So you can put in 0, 1, 2, 3, 4, 5. You can put any numbers you want in. Now, we got to go back and talk about calculus a little bit. And I showed you this last term, but this is kind of new. That was the shear equation, negative 780. And you may remember that I told you the integral of the shear is the moment. We saw that there was a relationship between these two. And by the way, this is 6.2. I'm teaching you 6.1 and 6.2 simultaneously. And so what is the integral of negative 780? Negative 780x plus C, which is actually extremely important. So I'm going to go add that back because this equation may not be right. Plus, I'm going to say B like it's a line only because I used C a little while ago.
And you might miss conditions at 0.
There's no 780x, half like 780 squared.
Yeah, now here the problem is, what are we going to do for B? Well, how much moment is there at x equals 0? How much moment is there? There's actually none. In other words, there's no beam to want to bend down. Does that make sense? There's got to be some beam sticking out to go and want to fall down. There isn't any moment there. Now there is 780 all the way across that. Remember, we said there was 780 all the way across that. But if it was right here, then there is some moment. But if you're actually at zero, then that x is zero, the distance is zero. And so in a sense, you might say, oh, we got lucky then. It really is just negative 780x. But that plus b is going to matter. Like we're going to need it in the next couple of equations and calculations. Now, because of that rather glorious principle, instead of trying to draw a picture of the complicated, what was it, 28? Instead of trying to draw a picture of that next complicated section, I'm just going to take the integral of that previous equation. What's the integral of 5928 minus 312x? What's the integral of that?
5928x minus 312 divided by 2x squared.
Yeah, that x is x to the first. It's still minus. So the x to the first gets raised to x to the second, and then you divide by 2. So the 5928 would grow in x because it's x to the 0. And the 312, x would become x squared, then you divide by 2. 312 divided by 2 is 156. So there's my equation. Like that's the shear equation. I don't even have to like draw pictures and try to figure, because that's kind of complicated, right? Like didn't we sort of struggle with even making that equation for shear? And so I got to do the same thing for moment. Now, can you do it? Absolutely, you can do it. But let's just do it with calculus. So the integral of 5928 and I won't write dx in there, would be 5928x minus 156x squared, and then plus that constant. That would be the moment. Now, this constant is not 0. And if you just ignore that, you get this whole thing wrong. That's exactly right. Where did this previous equation leave us? This previous equation when m was 8, and remember that's where it ends right there. It goes from 0 to 8, and this is where the new load takes off, right? So if I figure out what m of 8 is, negative 780 times 8, I get negative 6240. So I can say down here that at x equals 8, m better be equal to negative 6240. Do you agree that that has to be true? This produces a, call that D, I'll call it B. I'll stick with what I said before and call it B. This is kind of like y-intercept. That's why I'm picking B. Y equals mx plus B. It's like the y-intercept of this graph, if you will. So this would indicate if you stick in 8 into all those equations and you put in m as negative 6240, and please punch this in really quick. Like I want to give you some think time. You get negative 43,680. I say that not to check my work because I check this a lot. I'm sure I'm right, but it's not a bad move. Now, I'd like to show you one other thing really quick. What does an integral actually do? I don't mean all the dumb formulas like the derivative of sine is cosine, the integral of cosine is sine, you know, all that kind of stuff. But it's like, what does an integral do? It actually tells you the area under a curve. Isn't that right? Stare at that shear graph right there. What are the units of that shaded area? The units. I'm not looking at the answer, but what are the units of it?
Uh,
It's pound feet. Isn't that what a moment is? That's why the integral of shear is moment. And if you wanted to know the area under that, notice that particular shape right there is triangles and rectangles. Does it make sense? You could just multiply and use like geometry formulas to find that. In this case, because that's a straight line. But the integral of a straight line is a curve. So I just took that line, that angled line right there, and it turned into a parabola. Because the area, and so that's kind of weird to think about, but it's like I could literally find the area into that without it. Interestingly, but just as a kind of an interesting thought, like that's why you take the integral of this. Logically, this was not somebody, and this is what I did when I taught it to you back in statics, but it's not just somebody going, hey, do you notice there's a relationship between, because remember when I taught this to you, we did not cheat and do this. We did it kind of by hand with simpler loadings. But like, what's the relationship between that V equation and that M equation? And we did it all by hand, and yet we noticed, whoa, the derivative of one is the other one. Is that an accident? No. Is that just a random discovery that somebody made? No. The area under a shear equation, because the units are pounds and feet, would be foot pounds. Therefore, the integral of a shear equation is a moment equation. Whoa.
So you got negative 43,000.
Unless I wrote it down wrong, yeah. Yeah, it's not wrong. Double checking. Again, you typing that in is actually better for think time than anything else. And I would actually really ask you to check if I was just calculating this with you, because I could push buttons wrong too, but I kind of checked it. All right, last one. What if we go all the way from 28 to the end? What's the integral of, that's weird, the integral of what? Zero. The integral of zero. Like, isn't that a list equation 0? What is the integral of 0? I think about area under a curve. What's the area under that curve right there? It's nothing. There's nothing underneath it. The integral of 1 is 1x. The integral of 5 is 5x. The integral of 0 is 0x. So 0. Yeah, and then there's plus a constant, right?
That's gonna be your original condition. Are your 28 put into the next equation?
That's exactly right. Now that last equation right there. So, what is this constant? Now think about it. That makes sense, because if the integral of 0 was like 7, isn't the derivative of 7 0? So the derivative of any constant is 0. So it's not just 0, but notice the graph said it literally is 0. You with me there? So just think about that. But anyway, yeah, let's go back to this. Let's go back to this equation up here and then like see where this is supposed to end. Isn't that what we did a second ago? Let's like figure out what M of 28 is. Again, slow down a little bit. What did we do a minute ago? We said, hey, where did this last one leave off? When it got done with 8, let's throw 8. Get out of there. Let's throw 8 into this equation to see where this ended up. Well, let's do the same thing here. Let's see where this one ends up by throwing 28 into it. What do you get when you throw 28 in for X there? Blurt it out and let's all agree.
Yeah.
0, is that true? I'm just writing down what you said, so. So at X equals 28, we're supposed to get M equals 0. So if this is our equation, M equals B, then B must be 0. So this equation literally is M equals 0. And of course that makes sense because the graph said there's no area under it, right? So it couldn't have been 7.
close.
Okay, to save a little time and also to make sure all the scaling stays the same, because it turns out these two graphs are a little bit related to each other. I'm going to copy this whole thing down there and just erase some of the stuff we don't need. I'm going to keep the stuff we do need and erase the stuff we don't need. Except for I didn't mean to erase that 8. And I want you to kind of be thinking about, like, as I'm sort of wasting our time doing this, I want you to be thinking about, okay, now what is it going to mean to go graph these? Again, these are more complicated graphs, right? More complicated equations. So there's a chunk of me that thinks, you know, I should be doing this in Desmos, man. This is like way less trouble. So
Well, yes, but is that 19 gonna be the vortex of the parabola in that area?
So you're wondering if the 19 has some kind of a play in this. I'll let that hang a little bit. So this was 19.
I think we'll have
Oh, so it is the vortex of the parabola. Question. Supposed to be 0, with 18, find 9 equals 4, must be a equation.
Okay, so let's take a look at this. So our first equation, and let's change this too. This would now be moment, and its units would be foot-pounds, but X is still feet, right? So everything else is the same. And so what was our graph? Let's see, our first one was just negative 780X. What does that look like? I don't mean like get your graphing calculator, but what does that look like? What shape is that? Straight line, but it has a slope of negative 780. So that means it's really steep, right? So if you go back here, like M of 0 is 0, but we said M of 8 is negative 6240. Does it make sense? That's going to allow me to graph that line without having to bust out my calculator. So the moment goes from 0 to negative 6240. So that means I was kind of a little hasty in erasing too much of this line. So again, I might have to change this, but basically it's going to go from 0 down to negative 6240. So it's going to go from here down to here. Now notice I've totally made this scale wonky. Remember, negative 780 is almost vertical. It's so steep. So notice across, I made this distance right here 8, and almost the same distance 6,000. Like I've totally screwed up but you're not going to be able to see this if I don't do this. And you should do the same thing in Desmos. You tracking with me there? So this is a straight line and it goes to right there. But then it switches to a parabola. Right now it really gets ugly because like, uh-oh, now what do I do? Well, I do know the parabola ended at 0, don't I? At 28. So it's like it landed right here. And so it ends up kind of looking something like this. I'm just going to kind of eyeball it a little bit, but this is hard to do. Like this is where, put you over on the other side, 8. And unfortunately, this is something I can only sketch. I can't do this nicely without software. And by the way, I am showing you something here. This is kind of a good way to sketch. If you just try to put your pencil on there freehand, it's always going to look terrible. So like just kind of, kind of work your way to it little at a time. And even though it's kind of rough, it's like, even though it looks like a haystack, like it's actually a pretty good trace. You see what I'm saying? Now, how do I know how high that went? I have no idea. No idea whatsoever. Now, it does turn out to be true that the high point is right above 19, which is what Caesar was saying a little while ago. The location for minimum shear 0, will be the location for maximum moment. As it turns out, if you put a weight here, like a bunch of weight on this beam, it's going to crack from shear right there. because there's going to be mega force right here because this is the only two places pushing up. So there isn't anything pushing up here. Well, it's pushing right there. It's going to crack either right there or right there. That's where shear will happen. Where's the moment? Where's it going to break if it goes like this? In the middle. So out here, there's actually no shear at all because there's nothing pushing out there at all. But that's where it's going to break in the middle. So the location for minimum shear, zero shear, is actually the location for maximum moment every time. That's actually a ridiculously rad pattern. It's always the case. So when I figured out 19 a little while ago, that's because I knew where the center was going to be. In other words, if you knew this, does it make sense you could actually go back to that red equation up there and throw 19 into it? And you would actually know what that moment is. Now, if you have a graphing calculator, you know, or Desmos, do you need to? No, just graph it and then go say, what's that top number up there?
Your equation, take the derivative of that, which brings it back to the other one. And then
Yeah, everybody track what he just said? Don't you find high points by taking the derivative of that m equation and setting it equal to 0? Because that's where the slope of it at the top from calculus, the slope up there is 0, isn't it? So let's take the derivative of that. Wait a second, we already did. That was the shear. We already took the derivative. That was the shear. And set it equal to 0. We already set it equal to 0. Like, you see why it's 19? Like, that's pretty rad. Like, that is not just a pattern. Like, this is what calculus is. It's just insane. You should have a chill going down your spine right now. So plug 19 in there. Well, you throw 19 in there, guess what? You get 12,636. It's kind of that maximum point up there. And then the last part of this just goes across. I'll kind of darken it in so you can at least see I graphed it. So there's your moment equation. So, you know, in the end, what are we looking for here? We don't really care about this. Notice there is a moment down here, but it's only 6,000. And that one up there is 12,000. So that's the one we need, right? So I can say now that my M max is equal to 12,636 foot pounds. No, just foot pounds. It's just foot pounds.
all the moment, the area would be these squares.
So just for the fun of it, write those two numbers down. Write down our V max, 3432 and 12,636. Write down those two numbers because we don't really have time to start something else anyway. So I just want to show you something really fast. So that's why we did the shear moment diagram. Really powerful. Find those two maximums. But let me pull up that beam page that I've pulled up before, if I can find it quickly, which I think I can.
What was the shear units again? Was it
Just pounds. I should have written that in there. Notice.
Oh, no, 3, 4, 3, 2.
So we have successfully figured out how much shear and moment that beam is under. And now, and we even know where it is. Isn't that cool? Where is that big shear? Like, I don't know about you, but I forgot. 3432. Where is that? At 8 feet. Where's 8 feet? Right at that joint. Of course it is, because that's where it's being pushed on. That's what's going to break it. It's not going to do this out in the middle of nowhere, right? It's going to do it where it's being pushed on. Of course it's there. Like, you could actually know in this problem, it's either at A or B before you even start.
780 on the right side.
Yeah, 780 is working A harder. So in a sense, you could have known logically it would be at A from these two calculations, like that one's more. Now we couldn't have known what it was, but we know it's over there. And then of course, the maximum moment is in a really weird location. It's nowhere. It is out in the middle someplace, but notice this one wasn't loaded symmetrically. So it's not just in the center. If it was loaded symmetrically all the way across, it's in the middle. You don't even have to think about it. But when it's loaded weird, like this one is, because it did have a distributed load on it, but notice it's not even in the center. And then there's a 780 on one side and there's not on the other. So it's like, where is it? You know, where's it actually happening? I don't know. Without this calculation, we wouldn't have went, oh, it's at 19. It's at 19 feet. That's where it is, which is kind of in the middle of nowhere. That's no place in particular. It's not even in the center of that load. It's not even in the center of that distributed load. You're seeing it. This isn't going to be terrible. I'll be able to find this in a reasonably short period of time. Let's see. Did I save it in this class somewhere? I'm pretty sure it's in statics. Let's go look in statics. Hello. So this is what you pulled off the shelf, perhaps at the tour, Western Specifier Guide. I'm going to go to the beam page, which again, I've shown you before. I think I've been there enough times, I'll recognize it even grayed out like that. Could be this one. No, it's BCIs. There it is. Okay, what are we looking for? Allowable shear, allowable moment. Like you, again, should be chill going down your spine. Like we're now literally picking a beam that is going to work. So, and of course, we don't want to just go to the bottom and go that one, right? Because that is an expensive product. It's 5 1/4 inches wide. It's 24 inches tall. Will it work? Yeah, 23,000 pounds of shear, 120,000 pounds a moment. It's going to work great. That costs a lot of money. By the way, notice this number right here, 32.4. I think that's how many pounds per lineal foot that beam weighs, which we would have to be adding to this. And by the way, moment of inertia, you now understand everything you see up here now. The width of the beam, the depth of it, how much it weighs in pounds per foot. You know what shear is, you know what moment is, and you know what I to the fourth is. You got it. You got it all. Where's the first one? You basically start from the top and you go until you get there. Well, let's start with 34, 32. There it is right there. Isn't that the first one? You agree? So let's pick that one. 1 3/4 by 11 1/4. Perfect. What's the problem with that? What's the allowable moment? 8,000. Everybody died.
But we would also need to hire.
Correct. That's right. We want to factor of safety, but remember what we saw at that plant? Did they perform as advertised? No, they perform double as advertised. So we actually really don't. But when I'm speccing it, like, I mean, I'm not going to go down and choose the bottom one, but I'm there. I'm always very careful. It's like 99.9%. It's like that does work, but I typically don't choose that. However, there's a huge factor of safety built in by everybody that touched this along the way. And so I know that I'm good. And even then, when it fails, it actually fails in deflection, which doesn't break anything. It just bends too much. Breaks some tiles. So, okay, so this one doesn't work. Do you agree with that? So apparently moment is like a tougher number. So now we got to go down and find a moment number that's 12,636. There it is right there. There's our first beam. Do you agree with that? What are we speccing? 1 3/4 by 14. Is that the only choice? Now I want you to think about this for a second. 1 3/4 is only that wide. That's a really narrow beam. That's actually a weird beam. So what if we went to the 3 1/2 inch size, which is kind of a normal wall? What if we went there? Which one should we pick? 9 1/4. So a 3 1/2 by 9 1/4, that would actually be a realistic choice for a real beam. I mean, is that rad? Like you're doing engineering now. Like this is how you're going to get paid 90,000 a year when you get out of your degree, because you can actually do this and be confident that it's right.
I wish this had like a price. Like the 3 1/2 and 9 1/4.
Right.
Seems like the more realistic beam, but is that a more expensive beam?
Very good point.
Does it matter if it's weird if it doesn't get the job done?
Yeah, I mean, they don't make many of the 1 3/4 ones for that reason. So sometimes it could be more expensive, and some of it's just based on volume. Like if you took that 1 3/4 by 11, whatever it was, and you did the section area of it, it could be that is less area than the 3 1/2 by 9 1/4, and so it weighs less, and at least in terms of price per pound would be cheaper. But if they don't make very many of those, then it could actually cost a lot more. Because the 3 1/2 inch size is like the garden variety one, they make a bazillion of them or whatever. And so, yeah, that's not that's definitely not out of the question, but it's kind of cool that there's actually, you could choose a beam in almost every one of these categories. Could you choose a 5 1/4? Yep, that one right there, 5 1/4 by 7 1/4. If you had some reason why 9 1/4 was too tall, you could go wider and shorter, and then it would maybe be out of the way of something or something. I do that all the time, constantly do that.
The momentum's on the. I know it's right on.
Oh, actually, yeah, the moment actually doesn't quite make it, does it? Because it's 12,636 and this is 12,566. Could you get away with that? Yep, plenty close enough. There's a factor of safety. If I had some reason for that. However, if I spec this with BC Calc, it's going to turn red and it's going to say it's over by 0.1% or something, and then it'll get kicked back. And so I kind of won't be able to do that.
It's weird that the height is shorter. When they test it under like compression, do they do it?
No, they do it the direction it goes, which beams are always standing up. You never lay them flat. And it's very different because the grain pattern does not want to do this, but laid sideways, it wants to do that. So notice this, remember this moment of inertia, how it was the width times the height cubed. So if you laid it sideways, that's not even the right number. That 1677 is assuming you're putting the beam in. Well, notice what they called it up here. They said this is the depth of the beam. If you turn it sideways, then you've not done what it said. They're purposely calling it that to not go to jail, if you will.
Okay.
So that's an excellent question. So let's look over here. Modulus of elasticity, check. Horizontal shear, talking about that in the next section. There's some stuff in here I don't understand. Tension and compression parallel to the grain. There's some things in here I kind of understand, but I don't understand completely. I think we're right there. And actually, I think bending is E times I. If I remember, I can't remember.
I was gonna ask about grain, because I never saw any like beams coming out with vertical grain.
Correct. Yeah, you're not going to see that because the beam wants to snap like this,
Yeah.
right? And if you had the grain pattern in there going this way, then it's just going to go and come right apart. Like that's
So
not a
like-
good direction
I
to
was like,
put
why
it.
is this even? I guess if we put, because now the grain is more look that way.